This was the original title that I sent, and and this is the title that they posted. Yeah. So now I change it to maybe this one. Yeah. Yeah. So the weather is very nice. So I took this picture earlier this week here. Yeah. It's very cold. Yeah. So.
That's in the main palace, right?
Huh?
That's in the Gromov-Witten?
That's in.
Did you take that picture in Gromov-Witten?
In this palace, yeah. You took as maybe someone else, because I went there last time too, but that was in the summer, so this time in the winter. Yeah. Yeah. So you'll see many of these pictures here because it's in every single page now. All right. So the topic is about partial Frege varieties. To begin, let me first explain the geometry of the space, and then how to compute the Gromov-Witten invariant and so on. So let's make sure that we explain, you all understand the space well. So the space X is G over P, where G, so G is a, it's to change another pen. Let's say this one. Okay. So G is a semi-simple Lie group, like SLNC or GLNC, and B is a Borel subgroup. So in the GLNC, there's just the upper triangular matrix, and P is just any closed subgroup containing B. Okay, so those are called parabolic subgroup. And P is parabolic. Make sure that G over P is a compact complex manifold. An example of those space include projective space, Grassmannians. Those are partial Frege variety or the full Frege variety. We will see a lot more of this last example. So this is, as I said, it consists of all the Frege of linear subspace of dimension 1 inside dimension 2. Okay, so that is the set F3 Frege variety. So the aim of this talk is the twofold. First, we will compute give an explicit formula to compute the genus 0 three-pointed Gromov-Witten invariance in terms of for both G over B mostly, and we'll also explain the same method work for G over P. In terms of Frege variety or Grassmannians, those are the quantum analog of the Littlewood Richardson coefficients. So that's why we call it the quantum Littlewood Richardson coefficient. And the second objective is to explain a quantum analog of the Larreyster spectral sequence from the vibrations relating the full Frege variety and the partial Frege variety. Okay. Of course, this to us at the beginning is a bit surprising because quantum cohomology usually do not have functorial property. So this is a situation rather special that we can get an analog of this one. Of course, we do that, meaning that this is a joint work with my former student Changzheng Li, that now he's in KS now. So mostly his work basically. So to begin, let me first give some more explicit understanding of the space. So let's start with the standard Frege variety. So these are just the set of all Frege inside Cn. So the Frege meaning that a net of linear subspace, one including inside another bigger one. So dimension of Vj is J. Okay. So as the way that we write as G over B in this case is like this. So it's GLNC divided by the Borel subgroup, which is, you can choose it to be the upper triangular matrices. And you also have another description in terms, once you choose the metric, you can reduce it to the maximum compact subgroup. You can also write this as UN over U1 to the power n. So there are two descriptions. And partial Frege variety is just similar. Let's assume just a two-step Frege. So you can do it in general. So instead of the full upper triangular matrix, you will replace it by the upper triangular block matrices. Okay. So in terms of the UN, you divide it by product of the UNIs. So example, similar to Grassmannians in general or projective spaces. So those are a typical example, the flag and partial flag variety in the A type. So the group is SLN in this case. So in general, this dual description of the flag variety continue to hold true. So you can look at flag variety, you can write it as G over B, or you can write as in a compact point of view, it's K over T. So K is the maximum compact subgroup of G, so like UN inside GL and C, and T is the maximum torus inside K. Okay. So this is a way to see the space as a compact space. Okay. So of course T is also the intersection of the Borel subgroup with the maximum compact subgroup. So K is the maximum compact subgroup in G. Similarly, for partial flag variety, what you do is you either divide by something bigger than B, or in a compact point of view, you divide something bigger than T. Okay? Of course, this bigger space H is just the intersection between P and K. Okay? So let's just draw this in this picture. You either look at a complex point of view, then you have this G, Borel, and then in the middle one is a parabolic subgroup. Or you can look at the compact point of view. So T is the maximum torus inside a compactly group, K, okay, and then the lower row is the maximum compact in the upper ones. Okay. So these are the spaces. But what will be more important to us is to describe this space by a different point of view. Is all this space are just the same as coadjoint orbit, okay, in the compact group case. Okay. So this description will be very crucial for us for all the description on the quantum cohomology later. So our space, we are going to use the compact description. So K is a compact group. The simplest example, let me start to do it in terms of example to give you an idea. What you have is the space is just CP1, or let's look at it as the quotient of SO3 by the maximum torus, which is SO2. Okay. So in this case, the group SO3 add on X is So the Lie group is SO3. The Lie algebra is more SO3. We use the Killing form to identify the Lie algebra with its dual. So even though it's coadjoint orbit, so sometimes in this case, let's assume it's adjoint orbit. So there's no difference. So this is adjoint action or coadjoint actions. So we all know that SO3 itself as a vector space is R3, and the Lie algebra is just the vector product. Okay. So the actions, what are those orbits? The orbit is just standard action. So the coadjoint action in this case is just the standard action of SO3 on R3 by rotations. So therefore, those orbits are just given by a sphere. Okay, so of which each radius. So S2 R is the radius. Okay, those parameterize the orbit. Okay, so therefore, in this case, the X is realized as a coadjoint orbit in this example. Okay, and if you look at instead of R3, you project R3 to the maximum torus, the Lie algebra of the maximum torus. Okay, so that corresponds to, you restrict the moment map actions from the whole group K to the maximum torus. So the moment map will so forgot to say that the space X sitting inside SO3 as a coadjoint orbit, that inclusion is the same as the moment map. Okay. So inclusion is the moment map. So you restrict the moment map to the maximum torus, then the moment map corresponds to you projections to the T directions. In this particular example, the Cartan subalgebra T is just the z-axis, the last coordinate. So therefore, this is the sphere, this is the coadjoint orbit, and then you do the projection, let's just call it F to R. Okay. And then what we will be looking at is these functions. It's always a perfect Morse functions on the coadjoint orbit. Okay. And the most important point is to understand where are the critical points of this Morse function. The critical points, of course, you see that the critical point, there are two of them. One is this one. Oops.
What is the origin of G?
G is just SO3. SO3. R. SO3 compactly group. LP3 here. G is a SO3C, for example. Yeah. Yeah. So K, we are looking at the compact point of view in this case. Okay. So the two critical points is the north and south pole, and the point is the critical point are exactly the intersections of the orbit with the z-axis. Okay. That's kind of key. And furthermore, those critical points are distributed very nicely. The north pole is the opposite of the south pole, okay, by the reflection along the equator. So that is these points that first the critical points are the intersection points in the T, and they are invariant under the reflection along the these are the old wall. This is not the new wall of conservative Solomon. This is the wall of the wild chamber. Okay. It's a reflection along the wild chamber, the wall in the wild. Okay. So the orbit is exactly one orbit under the wild group actions. So in this case, the wild group is just Z2 of reflections. Okay. So in this example, you see that the coadjoint orbit here, okay, has two critical points, and you see that the critical point are of index 0 and 2. Okay, 0 and 2. And then they are symmetric. Okay. So therefore, to describe this example, you don't need to look at the space. All you need is to look at so-called a diagram. Just look at T. Okay? And then you can read it off from these 2 points, which is the orbits under the reflection along this wall here. So once you have these descriptions, you see that the space can be decomposed using Morse theory of the gradient flow to be the union of two different cells. One is the cell corresponding to the minimum. The other is so this is one point. The other is a cell, which is a copy of C, which is the other critical point. So using this critical point, you look at the downward flow. So we label that by the W, which is the wild group action, the wild group element. So W gives you the reflection to get you another critical point. Okay, so that is the description in this example. In general, this is always true. So let me just to give you the next example to just give you an idea. So the next example is the full-fat variety. We will use this as an example for all our results to illustrate the results in all different fields. So the example is the space of all-frac. Okay. So of course, in this case, the space is quite big. X is 6-dimensional. And I usually have trouble drawing something in 6 dimensions, so you just think there are some internal space somewhere. Okay. So SU3 as a Lie algebra is 8-dimensional. Okay, this is the green thing. This green picture is the Lie algebra. Okay. Inside SU3, you have a Cartan subalgebra, which is R2. So we are drawing here. This is the Cartan subalgebra. So you can either sit inside here, you project to it because it's compactly grouped. Okay, and then you look at different orbits. And this orbit, coadjoint orbit X, I draw in purple, which doesn't look like a coadjoint orbit, but it cannot have enough dimension to draw. So anyway, the point is that the coadjoint orbit will intersect this vertical thing, this T, okay, transversely. Okay, and those intersection points are exactly the critical points. So what are the critical points? The critical point for the projections to the maximum torus, the Cartan subalgebra, which is R2, and then project to any linear direction. Choose one. Yeah, it doesn't really matter which ones. Okay, so those are the critical points. Okay, so in this case, you see that in SU3, this is the wild chamber structure in SU3. The Cartan subalgebra is R2. So the intersection point, you can just remember each chamber has 1 point. Okay? So in this case, of course, it has 6 points. The 6 points form one orbit under the reflections. So you see that under the reflections, this point reflect to here, reflect here, and so on. So you can label those intersection point or so-called critical point of this function. Of course, later they are just the Schreiber cycle, okay, by the element of the wild group. Okay, they give you the reflection gives you the critical point, and then under the gradient flow, they give you the generator for the cohomology group. So those are the Schreiber classes. Okay, so the orbit in this case is under the permutation group of 3 elements. The wild group is as 3. Okay. Just put some generic projections. Yeah. Generic projection. Yeah. So usually what you do is you pick a generic element in F. So for example, you pick a generic, so in T, so pick an element here. Pick an element here. And take the inner product with that element. And then the minimum will be this one. The point inside that chamber. Okay? So if you choose other element, there will be some other elements. Okay? So you have to choose a generic. You don't put it inside the wall. That's all you need. Okay? And then the index, you can also read it off. The Morse index are always like this. Each time you do a reflection, the index change by 2. Okay? So the example that I had, the first one, the index is 0. And then you do a reflection. So in this case, they're generated by two refractions, which we call S1 and S2, two wall. Okay, so therefore, when you do refraction for the minimum, you get indices 2, 2, 4, 4, 6, and so on. Okay, so that's 6 critical points. And once you use the critical point, you can do a gradient flow, and they generate a cell. And this is the cell. Okay, cell decomposition. So there are, so this is index 0. These are index 2. They're index 4, and this is index 6. Okay, so we are going to label all those Schreiber cycle or the closure of those cycles using the refractions. Okay, with respect to those walls. So the wild group, which are the chamber structure, describe all these classes, Schreiber classes. Okay. So that is what happened in general. Don't worry about the general case. Just think about this example that will be that would be pretty good. So in general, any flat variety can be described in terms of coadjoint orbit, and in fact partial flat variety too. And then X will have a decompositions. So in general, you can write as this so-called Buchar decompositions, BWB over B. Okay, and those are exactly the cell that I'm just drawing in terms of the critical point. So you can they generate the homology. Okay, so you use a downward flow, they generate homology. If you reverse it to get an upward flow, they generate the cohomology. Okay, Poincare derivative. Okay, so either use a downward flow or the upward flow. They give you homology and cohomology classes. Okay, and again, you can do the same thing for partial flat variety. The only difference is what are the partial flat variety? The partial flat variety correspond to not choosing a generic element to do the projection. You choose a element which are like this one, for example. Choose this element as I just mentioned here. Okay, in this case, then basically you only get 3 critical points. Okay, so those are the partial flat variety. You have less critical point in that case. Okay. Okay. So that gives you a basis. The basis, a good basis for the cohomology group. Okay. Now the next question is what is the classical ring structure? And then of course our aim is to understand the quantum product. Okay. So to describe the classical ring structure, which is a classical problem, very classical. Okay. So you can, as an abstract ring, Borel has they have a description of it many years ago. But more enumerative question is to understand exactly the intersection number. So those are these questions that the cup-product of any of these two Schreber classes, if you express again in terms of the Schreber classes, what are the coefficients? So those coefficients we'll call N, U, V, W. Okay? Remember, U, V, W are the wild group elements. Okay? They label the cohomology classes. And those are, in the case of Grassmannians, they call it little Richardson coefficient, and sometimes people still call it so in the other cases, but other people object it and call it a Schreber structure constant. Well, it's just intersection number here. Okay. So of course, there are just so many classical results here in terms of Conan Leung diagram. A lot of combinatoric description of this. Won't be able to describe all of them here. And so instead of just counting, those Coston and Kummer in 1986 give you some explicit formula for doing it. I mean, this is for all flat variety, partial flat varieties, not just GLNC. Okay, and then later Don Haibao in 2003 give a more reflective algorithm computing it. Okay. So lots of study. I mean, I probably have forget many important contributions, and this, of course, in fact, many everybody here. Oops. There's a quantum effect here. Okay. All right. So just quick description. So this number is described as the following. Is just you look at the Poincare deal. So this number you can describe as the intersection number. Is you look at these Schreber classes and then look at the Poincare deal of the sigma W of these three classes, and then the intersection, the integral of those classes is this number. So in terms of the enumerative question is you look at the Poincare deal of these three, sigma U, sigma V, and sigma W, check the Poincare deal of it. Just count how many points that they intersect. Okay? The honest intersection number of intersection points when they move so that they intersect transversely, and that is this this number that we want to count classically. And quantum on the quantum world is we consider them intersect whenever they are not really intersect, that they intersect with the help of a holomorphic sphere. Okay, so the holomorphic sphere will touch this free cycle at three different points. So that's why what we are computing in this case in the quantum setting is this so-called quantum product is related to counting the holomorphic curve, genus zero holomorphic curve with three pointed. Okay, so that's the formula that we will be discussing now. So of course. The pioneer work by Kim that he described as quantum cohomology in terms of a total lattice. And then there's also more recent result by Lam, and I think I have misspelled his name. Shimu Song. This is so the name, this name probably have to add some quantum correction here. Probably spell it, yeah. So this is a conjecture by Del Peterson that the quantum cohomology of the full, so these are full flat variety, okay, complete flat variety. It is a ring. It is isomorphic to the homology of the base loop group of the compactly group K. Okay, we'll explain more of that later. So what I will explain is to give an explicit formula for this number. Okay. With the help of this result of Lam, of course. Yeah. So this is a result. So the result is this is the case of full flat variety, G over B or K over T in the complex setting. Again, so you look at UVW in the wild group. So again, they label the critical points, right? And the same as they label the Schreber classes. So we want to count the intersection in this quantum sense. And you look at those representing the homology class lambda. So lambda is in H lower 2. Okay? So they represent, those number of holomorphic curves representing this class lambda. So this number is given by this formula. Okay? So I'll explain that later. So, so the lambda has to satisfy this row with this standard element and leave here with this half sum of the positive root or something. This is just to make sure that the dimension is right. Okay? The dimension of the moduli space has a correct dimension. And only in this case, otherwise it's always 0. And the formula in terms of this combinatoric data called C and D. Okay? So C and D, they are defined earlier in combinatoric, in fact, in Costin and Krummer and other papers too. I'll explain that later. Anyway, so explicit formula is a formula of type CCD. Okay. So let's just give you a description in this our example. The flat variety, full flat variety in C3, okay, FL3. So in this case, I've shown you this this example. So so this is the descriptions of all the classes or all the critical points, right? So in this case, we choose 3. One is S1, S2. U is S1, S2, and then the point credit due is sigma S1. So that means that you look at, oops, sorry, here, right? The cell corresponds to these critical points. And then V is S1, S2, S1s. Okay, so it's H upper 6. So due is in H lower 0. So that is just 1. So that corresponds to this point. Okay, and then the last case is the W is S2, but then you have to look at the point credit due. Okay, so that again is in H lower 2 because you look at point credit due already. So that corresponds to another one, sigma 2. Okay, so look at these 3 classes, and then we want to compute this invariant. Okay, in fact, you can in this low enough dimension, you can write down the whole table. This is the whole table. It's not very clear because it's not supposed for you to be able to see it. Okay, just so this is a table. You can write down the whole product. I mean, this is a table of all the product. And we're just computing this term. It's just one of the kind of non-trivial terms of Q and Q2 and so on. Okay. So so let's just slightly describe this a little bit geometrically. How do you see those holomorphic curves? There's only one, in fact, in this case. The coefficient is 1 here, a particular one. And the first constraint is that you have to, in this class, what does this class mean? Okay, because the holomorphic curves have to hit that one, right? So that hitting that, meaning that you have to fix a surface because the flat variety parameterize or lie inside a plane. Right, in C3. This is the set of all lie inside a plane. Okay, so a sigma S1 is represented by those pair which the S is fixed. Okay, similarly, sigma S2 are the set of all those S and L and S, those pair, such that L is being fixed. Okay, and this one, of course, is both L and S are fixed. There's only one element there, so it's L and S are fixed. So how many holomorphic curves, counting those, discrete number of those. So you want to count the number of holomorphic curves in X. Okay, so that is the family parameterized by T is a family of lie in plane inside C3, right? And then such that at 0, at 1, at infinity, they lie inside this 3 cycle. So that means that at the beginning, the surface is fixed. At the end, the lie is being fixed. In the middle moment, both line and surface plane are fixed. So you can look at the following. When you projectify the questions, projectify the picture, the line in C3 is the element in P2, and the plane is the element in P2 due. Okay. So now you want to have a line so that the corresponding projection to P2 and P2 due will have this picture. Okay. At the beginning, it hit the line, and then it hit this point and this point, and this is the other way around. Okay. Of course, you see that basically there's only one such, but that is 1, exactly 1, and there's only this particular class of this class have exactly one. Otherwise, the other class all have a bigger family or none. Okay, so that's how you see that in this particular case. You can see that to really count the discrete number of such family of such holomorphic curve, there is exactly one such curve. Okay, and the particular class has to be in this particular class. Okay, so that is it. Just saying that in low enough dimension, this sometimes can be seen directly. Okay, and so that to verify this formula directly. Okay, but what is the formula set? So the formula set, this number is in terms of this description C, C, and D. Okay, so let me just show you a bit this one. This before explaining that, let me just give you a few remarks. First, the formula work for a full factor variety G over B, and there's also similar formula work for G over P. Okay, I mean, this is a bit more notations. And also you can do it in equivariant versions with respect to the torus actions. Okay. And Mihail in 2007, in fact, I will explain some of this later too. He has some general algorithm of determining those, but in this we give a explicit formula for computing it. Okay. Yeah. Yes. I think I missed some pages. Just sorry, let me just I'm missing pages. Yeah. Okay. Back to that explain. So okay. So here's a definition of C and D. So C and D are element in the following. Those elements lower index are X, Y. They are element in the alpha wild group. Okay. And you'll see later that instead of element in the wild group, you really have to look at the equivalent class under the classical wild group equivalent classes. So you'll see why that is the case. So basically, in terms of up to these equivalent classes, each element, you compute that one. And what are those? C and D are slightly a bit related. You write down X and Y. First of all, in this case, you write down the X as a number of refractions. Okay. So, and then inside those refractions, so once you write down X, in each way you write down this refraction. Over there, you choose those to represent Y, basically, in some way, product of this. And then have some reflection and then do this. As a combinatorial construction, it would be very difficult to just get a good feeling of it in 1 second, anyway. So Y is kind of similar. In this case, you sum over the family, and then you do a expression in Y, and then choosing some of that element to get the X. Okay, let me just show you in some example, see how this works in action. Okay. So, in our example, U is S1, S2, V is S1, S2, S1, W is S2. Okay, sigma lambda is this class. So the thing that we are computing is this one. Okay, those are in terms of CCD. Okay, don't worry about exactly what those are. And then the answer will be this, and you'll see why that are the case. Okay, so let me just for simplicity, just show you this particular last one, the D one. Okay, the answer was this minus the alpha 2 theta square, and you can. This is the formula. So what does this really count? This count the following. Remember, this count the following. So this is the. We'll show you why this alpha chamber structure will come in. Okay. The chamber structure is the following. You have the original wild group, but then you also have this horizontal line. So why are those? So why is this alpha wild group? Okay. So we'll explain that now. The reason that the alpha wild group come in is the following. That in the quantum cohomology, besides the usual cohomology, remember the usual cohomology are labeled by classes. The classes are labeled by W, the wild group. Okay, but in the quantum cohomology, you also need this lambda thing. Okay, lambda is in H lower 2. In H lower 2. But here, there's a special property in this flat variety is because H2 is the Cartesian subalgebra, and W is the wild chamber inside H2. But element in W class, they label all the cohomology. Okay, so yeah, so W is labeled all the cohomology classes. Yeah, so but the thing is, element in W is the reflection on T or T star, whatever. Okay, so you add on the T. And then so W add on T, and H2 it's just a vector space. It's just a translation anyway. Okay, so you can consider the semi-direct product. Okay, so one is reflection, the other is translations, and then the product is the alpha wild group. Okay, it's just a wild group semi-direct product with Q. Q is just H2. Okay, Q is just H over 2. Okay. So you see that why that's why one instant you see that why the base loop group come in, because this relation, you will see that. And the thing is, if you do two reflection, that is the same as one translation. Okay, reflect and reflect is a translation. Okay, so for example, you see that so these are all the reflection along the wild wall chamber, right? But then to get the alpha wild group, all you need is to add one more reflection, because reflection plus reflection is a translation. Okay, so it's reflect along this line, this one. Okay, so that is the reason is this reflection is the same as a reflection with respect to alpha 1 plus alpha 2 together with the translations. Okay, so therefore the alpha wild group can be described in terms of the usual classical reflection together with just one more reflection along this horizontal line as 0. Okay, that generates the alpha wild group. So now once you have that, you will start to label those elements. Just choose a wild chamber, so in this case called wild alcove, this one, the basic one. You reflect by S1, so you just label by 1. Reflect by S2, reflect by S0. Okay? And similar, this is reflect by S0 and then S1 and so on. So you can label all of this alcove in terms of this label, and just which reflection. For example, this reflection is 1, 2, 1, 0, and so on. So, very good. So let's come back to compute this C and D in this example, computing D. Okay, look at in this D, you see that this one is 1, 2, 0, 0, 2, 1, 2, 0. Okay, they are in. So look at those reflections. Okay, so one is here, the other is here. Okay, there are two different classes. One is reflection. So once you have this, so this is this 2, right? Okay, so one is X, one is Y. Okay, this corresponds to this reflection. We want to compute a D. In this case, D is minus alpha 2 theta squared. Question is why? So the idea is you try to go from this standard wild chamber. One way to go here, the other way is go there. We'll compare them two. Let's look at it closely. So you start from this fundamental chamber alcove, in fact. So this is 1, 2, 0, the other is 0, 1, 2, 1, 0. So this one, if you go to here, you reflect along free wall, 1, 2, 3. You hit this free wall. Okay. Now, another way is you go from this one to that element. You can go this path, or you can go that path. That corresponds to different reduced expressions of the work that you can express an element. So, for example, you choose this one, this path. So if you choose this path, then you do this reflection first. Then you see once you do this reflection along this one, this line will go to here. This line will go to here. Okay? But this one doesn't. And then you go to another reflection along here, then this final line will go there. Okay? So in this longer expression, you pick up those elements correspond to this free wall. Okay? So then that will count. How many? Well, this one will contribute. This is a reflection for alpha 2 minus. This one is the one theta. The horizontal line is theta. The other one is also theta. Okay. This horizontal is theta, and then this is alpha, and then alpha 1 and alpha 2. Okay. So you count all those. So then for this expression, what you get is this particular one will give you minus alpha 2 theta squared. Okay. In this case, there's only one reduced reduced expression gives you contribution, all the other will be 0. So this is just give you a flavor of how to, what kind of computation, combinatoric that are involved. Okay. So, so let me just say a few words about the proof, which are mostly combinatoric methods. So what we really use is, among other things, is one of the is a Chevrolet formula, which is a pretty important role here. It says that the quantum product is determined if one is very simple. So this is a general element, but if this one is just one reflection, and then that is a formula, it's called a Chevrolet formula, and then you can write it in terms of a classical one, and then a quantum part. Okay. The reason is, in this case, you see that, in this particular case, you see that it's not too complicated, because the quantum part, in a way, look very similar to the classical part. Very similar. There's no very complicated term. And also, what are the things that you're summing over? Well, these are the classical ones. And the quantum ones are almost the same, except just shifted by these two rows, basically. That's counting the dimension of the moduli space of holomorphic curve. So that is, later you will see that all this phenomena, that's why G over B or G over P is much nicer. It's kind of related to that the structure is not as complicated as general case. Okay. So then once we use this, and then we also need to relate this to the work by Lam and this Sumusulu plus corrections to the Pontryagin structure on the homology of the loop group. Okay. And then some other argument. And then the thing is that once you are in the loop group, we know that loop group has a very nice expressions. Other using Morse theory by Bott and other people has a different basis. That basis is very simple. So you kind of using relation between various bases, and C and D are related to transformation of bases. So that's why the formula look like conjugations. Okay, CDC is a change of basis formula, basically. Okay. So I should give you a few remarks on the loop group. I think I will switch to talk about. Let me come back to this if I have time, because I will also discuss some familiar symmetry point of view by Peterson. I have 16 more minutes, right?
Not 16.
16. Yeah. I need to go to the banquet myself too. Just to be sure that I explain the second part, let me go kind of switch the order and come back to this later. Okay. Okay. So come back to that later. But here is our work start from the standard framework, the G over B, also work for G over P. Okay. And the reason is that, in fact, you don't need to do too much more work, is that because there's a Peterson, it's a comparison formula that was conjectured by Peterson and then later proved by Woodwork, that relating the two products. We'll describe that later. Okay. There are also a number of many people working on this area, many different work, which are, yes.
Is that clear? This n for B is always positive number?
Not from the formula, yeah. We don't see it from the formula, yeah. But geometrically, yeah.
Is there any formula? I know that the classical little Richardson coefficient, there are some purely combinatorial description in terms of counting some kind of islands.
Many different ways, yeah. Combing, yeah.
Is there anything similar to quantum one?
Yeah. This is a quantum question. It's much more difficult than classical question. Yeah. No, it's classical. We have just so many different ways of describing that. Right? Yeah. But not much in the quantum.
Is this quantum product in any way can be expressed in terms of kind of tensor product of representations and decomposing it?
Could be. I don't know, because it could be related to the loop group or something. Right? It's related to the loop group of the K, but not anything like that we know of. It is not at the moment. Yeah. I mean, classically, yeah, there are lots of those. Yeah. Okay, so yes.
So I don't know how the Bohm-Ship derive with this total lattice.
Yeah.
With this total lattice.
I was asking.
Can you recover?
No, yeah. I mean, also it's different. This is a computation of the invariant. I mean, so those are just a description of the ring, right? So it's a different question, yeah. Yeah. I mean, the presentation one in terms of that is not a trivial question to answer. Yeah. Okay, so the next topic, after skipping some of those mirror symmetry part, is to relate these two quantum cohomology. One is G over B, and the other is G over P. Okay. So this is the result. Let me just state the film. Suppose let me start with a filtration. Okay, so this is a net of a net of parabolic subgroup starting from B and then a bunch of those. Okay. Then we construct a filtration. So the number of filtration is depend on how many terms in between. Because just like in the classical case, if you have one filtration, then you get one special sequence. Okay. If you have more, then you get more and more bigger filtration. So we construct a filtration parameterized by z to the power r plus 1, okay, to call the filtration f. So the filtration, or not the classical one, the quantum cohomology. Okay, so just do it on the vector space, a filtration. The first result is that this filtration respects the algebra structure. Okay, it's a key result. I mean, it's algebra filtrations. Okay, and then there are a bunch of corollary things. So the first one is this the quantum cohomology of P over B. Okay, can be described in the following way: that P is PR. That's the last one. Yeah. So if you look at those elements, so inside the filtrations, you look at the one that generated by those elements where the last grading part is positive. Okay, the last grading part is positive. Okay, that turns out to be ideal. Okay, you mod out that ideal. That is the quantum cohomology for P over B. Okay, so of course we are not really interested in P over B as such, because P over B itself is a full flat variety, the relating partial flat variety and full flat variety. So here is another one. So assuming that P over B is a product of the standard flat variety. Okay. It turns out that this is most of the time that is the case, because you look at the Dinghe diagram, right? Most of the time you take out something, it look like a product of the standard AN type. Okay. So that is pretty general. There's only if you can look at most of the cases of this type. But in this case, you can describe the quantum cohomology of G over P. So the idea is to relate the two. So G over B is that the quantum algebra structure is inside G over B is the graded R plus 1 piece. Yeah. Okay. So what is that? That corresponds to the last that part, right? Just correspond to the last column, basically, last row, whatever you call it. Okay, that graded pieces give you the quantum cohomology of G over P. So inside the G over B, you have a filtration, and then only the last row gives you the quantum cohomology of G over P. Okay, so that is the relation that we'll get. Okay, you can also describe it as a subalgebra divided by ideal. Okay, from the first description. Yeah. So also you can also describe that the tensor product, just like the very special sequence, the graded pieces of the cohomology of G over B is the product of G over P and so on. But this we need to do a localization for this quantum cohomology. Okay. So I'll give a remark here first. The first one. So this remark is our method will work for all cases for a group of type A, or the group of type C with more work, and a group of G2. Okay? So G is any of this type, it works in all cases. And for the other two, in fact, most of the cases is of this type. There are some other cases, it's just individual cases, they probably will all work, but there's this individual checking which kind of tedious. Okay? So even the other cases is, most of them is, because when you take away things which are, most of the time it's just taking away things which are A type. You know? All right, and also this is a generalization of the Leray spectral sequence is when you set Q go to 0, this is the Leray spectral sequence. Okay, so this is a quantum deformation of the Leray spectral sequence. So you think that that may be quite simple, some deformation. It turned out that it's a bit tricky. Okay, let me just describe you this example again. In this Fair variety, okay, so we'll just copy this table that you have everything which you are supposed to read it, and then the filtration is this. This is a full Fair variety. This is a partial Fair variety. We're comparing this one and that one, and 5 appeal for B is CP1 in this example, and then in this case, the filtration is a Z2 filtration, and this is the filtration. To check that, you can directly check that this is the algebra filtration by using the table you can see. First of all, in the first part, this is a classical part. Okay? You always have a classical part first, and then you have the other part. And the way that to put it is not, well, anyway, this is the one. And so this is the last row, basically. Yeah. So you can see that if you look at this one, and then taking away all the bottom one, that related to the cohomology of G over P. Okay. So let me show you here. The column cohomology of G over P. This example is generated by those underneath the 0, 1, and then so this whole thing is subalgebra divided by this whole ideal there. So this is kind of the favor of the result that you get here. And the key reason that this has a possibility of working, of course, we don't expect that to work for quantum cohomology in general. But in this case, it really used this Peterson-Woodward comparison formula, which says the following. So the formula says that is relating, the formula is the following, is relating the quantum cohomology of G over P in terms of quantum cohomology of G over B. Okay, there's some formula, but the trickier part of the formula is you have to shift this W. First of all, you have to pick a, for example, if you want to compute this for G over P. Okay, first of all, you have to choose a suitable lifting of that one. That's a canonical choice of the lifting for any such element. This is parameterized the cohomology of G over P. You can find a particular one for G over B. Lambda B is satisfy this property. Okay, so that is a particular lift to choose this lambda, and the tricky part is you don't choose it for W. You have to do a shift of W. Okay, now this is the refractions of the longest root. Okay, so so it was indicating that you already see that G over B and G over P are related in the product. But then to construct the filtration is much more complicated. You have to really show that they respect the algebra structure. But of course, the main essential tool is to need to use this one first. Okay, and then there are lots of combinatorial argument involved into proving it. And okay, so we can come back to this mirror symmetry part. So that was the main result that I was addressing, these two parts. The mirror symmetry part is this. So that is just some conjecture of Peterson and later by other people. So you can look at the free loop space or the base loop space. Free loop space is Lk, and the base loop space is omega k. Okay, and Peterson conjecture the following, which was proved by Lam and I think this probably is by Sumo, is the quantum cohomology is ring isomorphic to the Pontryagin product on the homology of the base loop group after localization, inverting the Q. Okay, and the Pontryagin product is just because K itself has a product. We induce a product on the base loop group, so induce a product on the homology, and that's called a Pontryagin product, coming from the group product. Yes.
What does it mean? Where does the lambda ring go away from the left-hand side to the right-hand side?
The right-hand side have the lambda already, because it's parameterized by R5 loop group, R5 while group. So the left-hand side parameterized, the classical one parameterized by W. The quantum one parameterized by WR5 because of the lambda. That's exactly that was what I was saying earlier. It's because Q to the lambda include that. That is exactly parameterized by WR5. And those parameterize the Chebyshev class on the loop group. Yeah.
We do also have some condition about quantum cohomology or corresponding the same as a within the argument.
Yeah.
Is that what in some cases can be equivalent to this condition?
Not that I know of, yeah. I don't know. Yeah, I don't know. Yeah. I don't know how to do that for any general G though. That I think it's only for A type, okay? As far as I know. I mean, I could be wrong, yeah. So, so classical finite dimensional compact group, like UN, GLNC, this is a flat variety, okay? And this is a flat variety, okay? You can look at the quantum versions, loop group versions. There's some other central extension. Let's just forget those central extensions. Roughly, it's a free loop group, okay? And then this one is the GC and all this map, formal map and so on. So C started that. And then the thing is, when you do the quotient, okay, the analog of this is the free loop group quotient by T, which is not the base loop group. The base loop group is the free loop group quotient by K, right? So that's what I want to say. Yeah. So the full flat variety here is supposed to be LK divided by T here, the torus part. Okay. So the base loop group is LK divided by K. Okay. That is really correspond to a partial flat variety. Okay.
Which
Oh, next page. Yeah. Yeah.
the cohomology loop space is even dimensional. Cohomology loop space is even dimensional.
Cohomology of loop space is even dimensional. What do you mean?
You are targeting the cohomology loop space, base loop space, right?
Homology of the base loop space.
So this is even dimensional.
Infinite dimensional, yeah.
But the corresponding is time dimensional.
No, but the quantum part Q to the power lambda. Yeah. So if you compute the wrong color. If you compute the cohomology of K over T, that is those classes are labeled by W. But then you also have to have this Q to the lambda. Lambda is in H2. Now that is labeled by W semi-direct product with H2. You get the alpha wild group. That label the homology class of the loop group, base loop group. Yeah. Okay. Yeah. So back here. So W label this homology class. Okay. So wild group is this one. Right? It's a semi-direct product with H2. So this is this Elkhoff picture. Okay. But this one is really correspond to the full flat variety in the loop group case. It's the free loop space divided by T. But we want to do the free loop space divided by K, and then of course the filtration, fibration. And the fiber is K over T. So the fiber is a standard flat variety. Okay? So therefore, instead of parameterized by this, you will parameterize by this block, because you have to take away K over T part. Right? So therefore, now they are not labeled by each Elkhoff. They are labeled by block of Elkhoff. That's why in this CCD formula, when you have seen Y, you have to sum over the Y under the whole classical Y group, because you have to look at the whole block at the same time. Okay, that's what the difference. Okay, so yeah, maybe skip this one. So let me just explain that for a few minutes. So let me just use that one. So Peterson has a conjecture that in the Leung-Leung group, K-cat, K-check, okay, you can have a variety Y with a C-star action. The fixed point set, 1 correspond to, on the K side, the parabolic subgroup. So each parabolic subgroup corresponds to a fixed point set of a C-star actions. And then you look at the downward flow and upward flow. So those are the YP plus and YP minus. Okay. The thing is the YP plus capture the quantum cohomology. YP minus, this is a ring of functions, capture the homology of the loop space. Okay. So that is more related to the what we usually think about mirror symmetry, right, between A and B side. Right? But he also have a description for that one. So if you use these descriptions using that conjecture, you will get this one, which was proved by Lam and his co-author, because the whole space Y is you can look at the Y plus for B and Y minus for G. Okay. So that gives you this description as a corollary. And also it was a work of Richards that she in fact realized that the YP as a critical set of the natural space called ZP. So that probably more into the mirror symmetry point of view. So you can try to describe the cohomology, quantum cohomology this way too. But all these are still pretty much unknown. Yeah. So let me just stop here. I don't think I have time. But thank you very much. I'll just say I enjoy this very much. This is